This work was performed at the request of and in collaboration with the Coast Guard's Marine Board of Investigation. I would like to thank the Coast Guard for the opportunity to participate in this investigation. Before beginning my presentation, I would also like to acknowledge the assistance and feedback from my colleagues at the NTSB, as well as these listed organizations. Today I'm going to present some results of the Materials Group investigation into the implosion of the OceanGate Submersible Titan. After some nomenclature, the presentation will be broadly divided into two parts. In the first part, I will describe what we have learned about the construction of the Titan's composite hull and the implementation of its real-time monitoring system. I'll briefly discuss the version 1 hull. I will then move on to the second, or V2 hull. This hull was manufactured using a multi-step co-bonding process that was different than the V1 hull in that it contains multiple adhesive bonded joints. We were able to examine some material from the manufacturing of the V2 hull, and we found several anomalies within the composite and the adhesive joints, including waviness, wrinkles, porosity, and voids. I'll show examples of those as well as some features consistent with rubbing damage at one of those adhesive joints. Next, I'll recap the Titan's real-time monitoring system. I'll talk briefly about the principles behind these methods and review how OceanGate implemented them on Titan. The second part of my presentation will focus on changes in the mechanical response of the hull following dive 80 and observations gathered from images of the wreckage on the ocean floor. I'll show that the Titan's real-time monitoring system detected the loud bang that we've heard about previously, and that the strain response of the hull changed on subsequent dives after the bang. I'll finish with some images from the Titan wreckage. These will show that the composite hull experienced substantial delaminations at or adjacent to two of the hull's co-bonded joints. Before continuing, I do need to note that the NTSB's own investigation into the Titan mishap is still ongoing, and as such, the scope of my testimony will be limited to factual information. Also, there is a significant amount of additional documentation that can be found in the NTSB reports. I'll begin with some basic nomenclature. So the first term to define is composite. A composite in general is any material made up of more than one material, but as applied to Titan, it'll refer to unidirectional carbon fibers that are embedded in and reinforced by a hardened polymer matrix. OceanGate utilized several methods of fabricating composite structures from unidirectional fiber. One was wet winding. For this method, the fiber starts out dry and is dipped into a liquid resin bath by the user at the point of use. The other is pre-preg. In pre-preg systems, the carbon fiber is pre-impregnated with resin by the fiber manufacturer, or often by the fiber manufacturer, and is often delivered as a flat sheet on a roll. It can then be split into tapes or tows. Here's an example of a pre-preg splitting operation. This is a comparatively small machine and would probably not have been sufficient for the amount of fiber that OceanGate needed for Titan, but it illustrates the idea of splitting. A rolled up sheet of pre-preg is loaded into the machine and is sent through a series of cutters, producing a large number of tapes or tows. The tows are then rewound onto individual spools. One of these individual tows could contain thousands or even tens of thousands of individual carbon fibers, depending on its width and thickness. The pre-preg tapes that we saw in the previous slide are clearly very thin, so objects built up using layers and layers of these tapes will have a laminated structure. One course or level of unidirectional material is a ply or lamina. I'll now discuss the manufacturing of Titan's composite hull. The Titan V1 cylindrical composite hull was manufactured in 2017 and was at the core of the Titan pressure vessel. The hull was manufactured using a combination of wet wound fiber for the circumferential plies and prepreg for the longitudinal plies. The ends of the cylindrical hull were capped by titanium rings called segments that were glued to each end. The segments in turn were mated to cylindrical titanium domes that were bolted on at either end, and the forward dome contained no affordance for the viewport. As previously noted, a crack was discovered in the composite hull and it was retired from service in 2019. Oh, too loud. Okay, all right. Investigators had the opportunity to examine a leftover piece of the Titan V1 hull. The hull was originally manufactured with excess material at both ends, and then the hull was trimmed to size. The leftover piece was trimmed excess material from one of those ends. The piece contained voids and delaminations. One notable delamination was located about mid-thickness and is shown from different directions in these two images as indicated by the white arrows. After OceanGate retired the V1 hull, they manufactured two 1/3 scale test articles. Just like the Titan V1 hull, those cylinders were manufactured with extra material on both ends, and then the cylinder was trimmed to size. One of those trimmed end pieces is shown in this image, and in greater detail in these images. Yeah, thank you. The trimmed end piece contained two notable wrinkles and a mid-thickness delamination as indicated by the arrow in the upper image. According to multiple former directors of engineering for OceanGate, both subscale test articles imploded or were on the verge of imploding at or below 2,800 meters. OceanGate identified these wrinkles as a likely cause of the low implosion pressure. In order to mitigate the wrinkle problem, OceanGate pursued a co-bonding process, which I'll describe in a couple of slides. After building a couple of test rings to test the viability of the co-bonding process, OceanGate proceeded with building a full-scale version 2 hull for Titan. The full-scale V2 hull was manufactured by automatic fiber placement. This is a robotic system that, in this case, was probably attached to an overhead rail and trolley system and contained multiple spools of pre-preg tape loaded into a fiber placement head. The head can apply multiple tapes in multiple directions. For the first two plies, the tapes were applied in the circumferential direction, like a spiral from one end of the hull to the other. For the third ply, the tapes were applied in the longitudinal direction. The sequence was then repeated until 133 plies, approximately 1 inch of pre-preg material, had been applied to the hull. The hull then proceeded to curing and co-bonding. The co-bonding process, or multi-cure process, as it was sometimes referred to by OceanGate, involved building up the composite hull in 1 inch layer increments. After the first inch of pre-preg was applied, the layer was capped by a peel ply. This peel ply was a plain woven synthetic fabric that was designed to be removed later. The assembly was then cured at elevated temperature and pressure in an autoclave. After curing, the peel ply was stripped from the surface. The act of stripping the peel ply is intended to create an active surface for adhesive bonding. After peel ply removal, bulges in the hull were removed by grinding. A layer of film adhesive was applied, followed by another inch of pre-preg, capped once again by a peel ply. The assembly was once again sent to the autoclave for curing. This process was repeated until a nominally 5 inch thick hull was produced. The image on the right shows a cross-section through a trimmed end piece of the hull. The lighter lines spaced about 1 inch apart are the layers of film adhesive used to join the carbon fiber composite layers. This image shows the rough V2 hull upon completion. The rough hull was manufactured with excess material at either end, which was subsequently trimmed off. The materials group examined trimmed end pieces and a recovered piece of the V2 hull and found waviness, wrinkles, and porosity within the composite layers and voids within the adhesive that joined the layers. The Titan hull exhibited waviness and wrinkles within the hull layers, especially the second through the fifth layers. The image on the left is an overview image of one of the trimmed ends. The image on the right shows a portion of the through thickness face under oblique lighting. The oblique lighting reflects off of the composite plies based on their orientation. The periodic light-dark reflections are an indication of the waviness of the layered structure. We examined the trimmed end in closer detail and found instances where wrinkles had been ground flush with the outer surface prior to the building of the next layer. The image on the left shows an example of wrinkle grinding. A thorough examination of one of the trimmed ends indicated that the number of ground wrinkles increased with each successive layer, peaking at 24 for the fourth layer. No grinding was performed on layer 5 as it was the last layer. It should be noted that the number of plies removed by grinding varied significantly. In a survey on a block of material brought back to the lab, the number of plies removed by grinding varied from 1 to 12. We also observed porosity between composite plies. This is an image of a single layer piece of the hull that was retrieved from the ocean floor. The side that is shown is the adhesive used to join two layers. The other side is painted, indicating that it is the innermost layer, or layer 1. The strip has been cut out to evaluate the through thickness material structure. Here's a macro scale image of the cut piece. The next slide is at higher magnification and shows the composite plies in greater detail. The higher magnification images reveal the laminate structure of the hull. The lighter gray layers are circumferential plies, where the fibers lie within the slide, and the darker gray layers are longitudinal plies, where the fibers run in and out of the slide. In between the plies, there were thin layers of resin that contained porosity. A higher magnification image on the right of the slide illustrates this point. Several examples of pores within this fine resin layer are indicated by the red ovals. The amount of porosity within these resin layers was estimated to be between 18 and 27%. Finally, investigators observed voids in the adhesive used to join the co-bonded layers. Some voids were present in all layers. However, at the interface between the first and second layers and between the third and fourth layers, some of the voids formed elongated structures in the adhesive. These structures were visible on longitudinal cross-sections like the one shown. The appearance and structure of the voids within the adhesive bond is illustrated by this laboratory fracture. A thin strip of hull material at the layer 1 and layer 2 adhesive joint was snapped open, and the resulting fracture surface is shown in the lower image. 3 distinct regions were seen on the fracture surface. The green regions are fractured adhesive. The vertical linear features are fractures through the carbon fiber composite. The checkerboard-like regions are thin layers of hardened epoxy that are above the carbon fiber composite but beneath the adhesive. The checkerboard patterns were left behind by the peel ply that was used during the curing process and then subsequently removed. The areas where you see this pattern were associated with the voids. Examination of the retrieved single-layer hull piece also revealed features that were consistent with rubbing damage on the adhesive surface. Voids were observed on the surface of the piece, like those observed on the trimmed end. As shown in the images above, some of these voids contained cream-colored debris that was readily removed with the tip of a fine blade and a synthetic bristle brush. The debris was collected and its chemical spectrum was analyzed along with a sample of the green film adhesive. As seen in this image, the debris and the adhesive had similar spectral peak positions and relative peak intensities. There were also physical characteristics consistent with rubbing. As shown in the image, and indicated by the red arrows, the adhesive exhibited rubbing marks that were oriented in the longitudinal direction. Next, I'll discuss the components of Titan's real-time monitoring system. This system comprised two sensor types. The first type, of course, was acoustic event detection, and the second was the monitoring of mechanical strain or deformation. I'll start by discussing the acoustic monitoring system. The Titan's acoustic monitoring system functioned on the principle that fractures and other forms of material damage create sound waves. These sound waves can be detected using acoustic sensors. These sensors are just tiny microphones that can be affixed to a surface and trained to listen for sounds associated with breakdown of the material. This is a complex but established field of engineering. The Titan's acoustic monitoring system comprised 8 sensors, with 7 attached to the inner surface of the hull and 1 attached to the inner surface of the aft titanium segment. On the hull, 2 were located at the forward end, 3 were in the middle, and 2 were at the aft end. The system listened for acoustic events that exceeded a predetermined amplitude, and when it detected one, it counted it as a hit and added it to a running tally of the total number of hits. There were 2 thresholds for the number of hits. The first threshold issued a yellow alert, and the second issued a red warning, at which point the dive was to be aborted. The amplitude and quantity of hits were established based on acoustic activity from the retired V1 hull and the Subscale test articles. Investigators examined acoustic emission data from dives in 2022, and when the data was analyzed, it was noted that 3 of the 8 sensors did not appear to detect acoustic events. One of those sensors was located at the forward end of the hull on the starboard side, and 2 were in the middle, as indicated by the red circles on the illustration. This slide illustrates the difference in sensor response. The slide shows 2 plots side by side of the forward acoustic emission sensors from dive number 76, which took place on July 6th of 2022. These are the original plots produced by OceanGate. Elapsed time is shown on the horizontal axis, and acoustic event amplitude and dive depth are shown on the vertical axis. The left plot shows captured acoustic events at the forward port side sensor, while the right plot shows acoustic events captured by the forward starboard side sensor. The latter sensor did not appear to register any significant events. Next, I'll discuss the strain monitoring system. Titan monitored hull strain using readily available metal foil strain gauges. As these gauges stretch or compress, the resistance of the metal foil changes, and hooking the gauges into a circuit and measuring the voltage drop across the gauge terminals enables the measurement of strain. The gauges were grouped into right angle pairs as illustrated on the right. There were 8 strain gauge pairs on Titan. 5 gauge pairs were located on the hull, and 1 pair was located on the aft segment. 2 gauge pairs were originally located on the forward dome during testing at the Deep Ocean Test Facility and may have been moved to other locations on the hull. As illustrated by the red arrows on the image, 1 gauge in the pair was aligned in the circumferential direction and measured hoop strain. The other gauge was aligned along the axis of the cylinder and measured longitudinal strain. On July 15th, 2022, Titan executed a dive to the Titanic, entered into the dive log as dive 80. Upon returning to the surface, the crew heard a loud bang, which was documented by the pilot in the OceanGate dive log and has been discussed at this hearing. This was the 14th dive to a notable depth for Titan V2 since initial deployment and the 6th notable dive of the 2022 expedition. The real-time monitoring system captured this loud bang, and it also captured changes in the hull's strain response after the bang. The audible event was captured as indicated by the acoustic activity plot on the left. The sensor shown here was located at the forward port side of the hull. The horizontal axis displays time, and the vertical axis, again, displays both acoustic event amplitude and dive depth. The acoustic activity increased upon returning to the surface leading up to the event, which is indicated by the red arrow. Several strain gauges also responded to this event. The graph on the left shows the hoop and longitudinal strain responses during the dive for group 4. As Titan descended, the gauge outputs increased in response to the external pressure as expected, and during the ascent, the output decreased as expected. Shortly after returning to the surface, the hoop and longitudinal gauges both showed a sudden shift in gauge output as indicated by the red arrow.
Lieutenant Steele, could we go back and try to get back on that page? It looks like it's not loading.
Okay, well, we'll just have to proceed, unfortunately. And so this is also presented in the materials lab factual reports. So if need be, interested in individuals can refer to the factual report. When plotted together, one can see that the sudden change in strain gauge readout coincides with the large acoustic event.
Dr. Kramer,
Yeah.
I think this is important. Why don't we take a 5-minute recess to see if we can get that slide to, show to function? Is there stages on that slide that should be loading?
It essentially shows both the, for whatever reason, it's not plotting correctly. It shows an overlay